we have to understand the geometry of what's going on between the cameras, and that's what we're going to start talking about today. So before the stereo thing, the stereo sections, we introduced projection, perspective projection. And here was the model that we used. In particular, we had a system where we had a center of projection that was located at the origin of a three-dimensional camera system. And then we derived from similar triangles the location on the image of the point projected down onto the image plane. And then in order to figure out where the point was going to land on the image, we just eliminated that last coordinate. Now, we said that this was a bit of an issue because this division by z was nonlinear. And because we had to pull out the particular z, it wasn't a constant z, it was the particular z. So we introduced this notion of homogeneous coordinates. And the homogeneous coordinates essentially added another component to the vector, and if it was 2D, it became a 3-long vector, 3D became 4. And the idea was that we were going to be able to convert from homogeneous to non-homogeneous when we needed it. But before we did that, all of our operations could be done through matrix multiplication, which, by the way, made homogeneous coordinates, the whole thing invariant under scale. I could scale a coordinate, homogeneous coordinate by anything, and when I did the normalization, divide by w here, it would go away. And one of the reasons we did this is we said that perspective projection could now be done as a matrix multiplication. So here I've written 1, 1, and here we've got 1 over f. And by the way, just to make life easier, I'm using the absolute value of z, so we don't have to worry about z being positive or negative. So when I do the multiplication, I get this homogeneous coordinate, and when I want to normalize and go to unhomogeneous, I get the uv by dividing it out. But in all of this discussion about projection, we have the notion of a camera's coordinate system. By the way, I'm going to go like this, and it's not some like weird curse in Georgia. It's a coordinate system, 1, 2, 3. Okay, so we have an origin and a coordinate system. And we said that we put the center of projection at the camera's coordinate system, and with the z-axis, the optic axis going down the z-axis. So to do geometric reasoning about the world, we need to be able to relate the coordinate system of the, I guess I'm going to have to do this. We have to relate the coordinate system of the world to the coordinate system of the camera. And in fact, today, what we'll do is the coordinate system from the world to the camera, and then today, I don't know when you're going to watch it, next month, the next lesson will be the coordinate system from the camera 3D coordinate system to the image. This whole thing falls under the labeling of geometric camera calibration. In order to be able for the camera to tell us about things in the world, we need to know the geometric relationship between the camera and the world. For reference, you can take a look at the Forsyth and Ponce book. The sections are listed here, and there's a nice description. So as we said, geometric camera calibration is composed of 2 parts. There's the first part that goes from some arbitrary world coordinate system, you know, put your origin wherever you want it to be, to wherever the camera is, and that basically tells you where the camera is in the world and its pose. And then the second one is from the 3D camera to the image plane. The first one is called the extrinsic parameters. That's the extrinsic. It goes from the world coordinate system to the camera coordinate system. The intrinsic, which we'll do next time, is from the 3D camera system to the image. So let's talk about camera pose, or the orientation and location of the camera frame with respect to the world. In this diagram, this transform T is a transform that goes between the world and the camera system. Okay, and that's what this T with lower w, upper C is going to mean. All right, we're going to talk more about this notation in a minute. The transformation that we're going to talk about is this going from world coordinates to camera coordinates. So that's a good time for a quiz. How many degrees of freedom are there in specifying the extrinsic parameters, in specifying the relationship between the world coordinate system and the camera coordinate system? A, 5, B, 6, C, 3, I mean it's three-dimensional space, or D, 9. Okay, well, let's take a look. This slide says for rigid body transformations, we need a way to specify the 6 degrees of freedom of a rigid body. So the answer was 6. But why 6? Well, you can easily think about it this way. Let's define a rigid body as just a collection of points whose relative positions to each other can't change. And for the mathematicians in the audience, we're going to pretend that's a well-defined statement, okay? Or you can think of it as a box. So the first thing I can do is I can locate that box in 3D. I can take one point of that box, say the corner here, and figure out the x, y, and z location of that box. So that's 3 degrees of freedom. Then I can take some other point on that box, let's say the corner, and I can move it around. Now I can't change its location in space arbitrarily because I'm holding this point fixed. So essentially this corner can move around on the sphere. So this point here can be moved around anywhere on the sphere. So this is supposed to be like rotated backwards this way. All right? And just the way you can think of on a globe from the middle, there's a latitude and longitude to get any location. There's 2 degrees of freedom of a vector's direction. So that's another 2 degrees of freedom. So we're up to 5. And finally, once I have this vector specified, I can rotate, I can spin about that vector. So the cube here, as indicated by this fancy Microsoft PowerPoint arrow that's in here, we can rotate it about that diagonal. So that's 1 more degree of freedom. So that's why there are 6 degrees of freedom for a rigid body. I'm going to assume most of you knew that already, but there you go. That's why there's a fast forward button. So now life gets ugly. I'm going to be using the notation from Forsyth and Ponce. It might not be the best notation, but it is a notation for dealing with coordinate transformations, which is what we're going to be doing. So the idea here is that superscripts are going to represent what coordinate frame you're in. So here I have some point P, and I've got the A coordinate frame. And the expression of the location of point P in the A coordinate frame can be thought of as a variety of ways. You can think of it as the location x, y, z in the A frame. But if you remember a little bit from your, I don't know, algebra, calculus, the right way of thinking about the vector that goes from the origin to P, that's this vector here, is it's got the I component of the amount x, the j component of the amount ya, and the k component of the amount za. So a vector is actually the sum of these 3 components, the I component, j component, k component, each scaled by the coefficients x in A, y in A, z in A. Suppose I want to express the location of point P, whose value I might know in coordinate frame A, but I'd like to know where it is in terms of coordinate frame B. Well, that's just a translation, and it's handled very simply by saying the location of P in B is just the location of P in A plus the location of the origin A expressed in the B frame. All right? And so that equation just gives us that new offset. And this OA in B, that's just a 3 vector. That's the offset of the origin of A in the B frame. I told you this was ugly, but we have to slog through it. The good news is, once again, homogeneous transformations, or I should say homogeneous coordinates, are going to come to our rescue, where translation can be expressed as a multiplication. So we've rewritten this top equation, P in B is equal to P in A plus OA in B, as this matrix transformation. A couple of things. First of all, that I, that's a 3 by 3 identity matrix. So this is, and since OA in B is a 3 by 1, this is a 4 by 4 matrix, which means that this vector down here, that's actually a 0 vector of length 3 transpose, so it's 3 zeros in a row. It's actually 0, 0, 0, and this is 1, 1, 1, 0, 0, 0, 0, 0. That's clear, isn't it? That's why we draw it this way, okay? And just to remind you, translation is commutative, okay? And you can actually show that in the matrix multiplication if you wanted. Now life gets uglier. Rotation. What I have here is a figure, or I think this is also from Forsyth and Ponce slides. And what I'm showing you is 2 coordinate frames, A and B. And you'll notice that A has an I vector, a j vector, and a k vector, and B has an I vector, a j vector, and a k vector. And one of the important things to realize is that this P value, the vector from the origin, can be expressed in 2 ways. It could be expressed as some components in the A frame times the x, y, z components, or some components in the B frame with the components in the x, y, and z frame, right? They're the same vector, right? And what's key is understanding that there are these basis vectors, and we need to know the amount of component that multiplies each of them. What we want to be able to do is say we're going to rotate the frame from A to B. And that's what this says. What this says is, given my point described in A, I'm going to have a rotation operator that will give me the P now expressed in the B frame. And R A to B means describing frame A in the coordinate system of B. And it says, so if you gave me the location of a point in terms of the components of A, this is, and it's only a rotation, after applying R, I get the components in the frame B. So what does R look like? Well, there are two ways to think about this. First, we'll think about it the hard way. R A to B expresses how each basis vector in A would be expressed in terms of B. So the first column of RAB is the component of the I vector of A expressed in terms of how much it has in the I direction in B, in the J direction in B, and in the K direction in B. So you can think of it as like the dot product between IA and each of the components of B, IB, JB, KB. And likewise, each of the following columns is that way. So one way of thinking about this is that the columns of RAB are the I vector of A expressed in the B coordinate frame, then the J vector of A in the B coordinate frame, and the K vector of A in the B coordinate frame. All right, so why is this true? Well, let's think about it this way. Suppose I had a point vector in the A frame, Harlem, that was just at value of 1, 0, 0. Okay? So what that means, it's actually a distance of 1 in the I direction of the A frame and none in the J and K of the A frame. What should the value of that be? All right? And I'll just write that down here. Well, this multiplies this to that. So it would just give me the IA dotted with IB. So the first component of the transform frame is just the I vector's amount in the I direction of B. Well, now let's go through this. We go 1, 2, 3. It's going to get IA dot JB. Okay, and again IA dot KB. In other words, I mean, it's just what it says here is that what we have to get out, if we had just a 1, 0, 0, needs to be how that vector is dotted with each of the components. And that's why this matrix can be thought of as having its column vectors as just being each of the basis vectors of the A frame expressed in terms of the B frame. Do you get that? So on the slides you'll have that, so just press the pause button and that way you can see what's going on. Just to remind you, I labeled this that the columns of the rotation matrix are the axis of frame A expressed in frame B. Why? Because we just went through all that nonsense showing it to you. By the way, it can also be thought of as the rows are just the column, are just the basis of the B vector expressed in the A frame, right? So here's IB in terms of the I component of A, here's IB in terms of the J, here's IB and K. So if you think about this, is that if I were to transpose that vector, so I made the columns the rows the columns, I would now have, instead of RAB, I'd have RBA, all right? This is an orthogonal matrix, right? The orthogonal matrix, all of the rows, all of the columns are unit vectors that are perpendicular to each other. So the determinant, so the magnitude determinant is 1, and it's your traditional rotation matrix. And by the way, really important is that the inverse is equal to the transpose. So if you had a rotation matrix and you want to go back and forth between the two, the inverse of the transpose, which realize it has to be because the inverse of RAB has to be RBA. And we just showed how the rows are the sort of the transpose with respect to the columns. So let's take a very simple example. So here I have two frames, and I'm telling you that the rotation of A to B is just about the z-axis. So the image on the right, I'm looking down on the z-axis. Now this should look very familiar to you when I ask you what is the rotation matrix. Why? Because you did this in algebra, right? You talked about just rotation of an angle theta about the origin when you were doing x, y. And hopefully you remember something that looked like this. See, it says cosine theta, minus sine theta, sine theta, cosine theta, right? George Thomas, who wrote the calculus textbook that many of us use, taught it to me as Charlie's little sister socked Charlie. That way you remember where the minus